Hello and welcome to our discussions on linear programming. Up till this point, we have talked a lot about linear programming, from formulation of linear programming problem to solution of a linear problem using graphical method to a solution of linear problem using simplex. Then from simplex, we advanced to certain other conditions, dual simplex, dual degeneracy, and so on. Now today we'll take up a new issue in linear programming, which falls under heading integer programming. Now what is integer programming? When you solve a problem using using simplex, or let's say graphical method, you often get final solution in fractions. For example, x1 might be equal to 21 upon 5, x2 might be equal to 7 upon 3. Now practically 21 upon 5 benches cannot be produced. 21 upon 5 or 7 upon 3 pens cannot be produced. I cannot place an order for 7 by 3 pens. So practically it is not possible to have fractions in our solution. But generally you might have observed that when we stop a linear problem solution, we reach the final optimum solution of a linear problem using simplex, or for that matter from graphical method. This final solution generally consists of fractions. What integer programming does is, it takes up that final solution and tries to optimize it in such a way that I get final result as integers. Because I cannot produce 21 by 5 chairs. 21 by 5 chairs is 4.2 chairs. 21 by 5 chairs. If you get x1 is equal to 21 by 5, where x1 is number of chairs, then this is not possible. What integer programming will do is, of course, I cannot take it beyond 21.5 unless I am compromising on some other variable, which might be x2. So how do I decide whether to compromise on x2, whether to compromise on x1, so that I get integer answers, so that I get integer solutions? This actually is 4.2. How do I ensure that I get either 4.2 or I may get a 5 or I may get a 6, 7, 10? But I need integers, because it is not possible for me to make 4.2 chairs or 7 by 3 tables. Maybe x2 is 7 by 3, making it 2.33 tables. This is not possible for me to make 2.33 tables. So what integer programming will do is, it will take up my final solution and try to optimize upon it in such a way that my final result is in integers. This could either go to 2, it could go to 3, it could go to 10, whatever value, but it should be an integer. And all my decision variables should be integer values. Yes, if in your solution there is a slack which is taking a fraction value, no issues. For example, I have x1, x2 and s3. Under B I am getting 4, 7 and 3 by 5. This is perfectly fine, because what I am interested in, producing chairs and tables. I am interested in resources x1 and x2, output x1 and x2, which is 4 and 7. So I have my solution as integers. x1 is 4, x2 is 7. This is final simplex table. So if x1 is 4, x2 is 7, perfect. We are not so much bothered about slack or surplus variables. So we'll try to solve this, and we'll try to understand the concept of integer programming from this problem. And yes, because it is our first integer programming problem, what we'll do is, we'll solve it using graphical method to see how we can improve upon what are the various options available. Why am I saying that 4.2 cannot go to 5? We'll see those things. We'll see such things using a graphical approach, and then from next lecture onwards we will try to solve integer programming using simplex. If this had to be solved using graphical approach, first of all we need to convert these inequalities into equalities and then find out coordinates where we could plot them. 3x2 is equal to 12, giving me x1 and x2. Now that we are studying integer programming, I sincerely assume that you have gone through the previous lectures where we have formulated a linear problem, where we have solved a linear problem using graphical method, where we have solved a linear problem using simplex method. So I'll assume that you have that basic knowledge. If you do not have that basic knowledge, you can go through this playlist. You'll find all those videos. Because now we are discussing different new issues, so I would assume that you are already aware of these solutions. How do we go about this? This is our first constraint. We have converted it into equality, and then if I put x1 as 0, x2 would become 4, and then if I put x2 as 0, x1 would become 3. So these two are my coordinates from first constraint. My second constraint is 6x1 plus 8x2 is equal to 24. From here I will be getting coordinates for my second constraint, and those can be found out. Making x1 0, I get x2 as 3. Making x2 0, I get x1 as 4. So these are first point and second point, first point and second point for first constraint, first point and second point for second constraint. This is what we have learned up till this point, how to solve a linear problem using graphical method. Then can we have our coordinate system? We have x1, we have x2. Our range is 0, 3, 4. So what we can do is we can take 0, 1, sorry, this will be 1, 2, 3, 4 and 5. Then this will be 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Now when I go to plot my first constraint, these are the points. First point is x1 0, x2 4. x1 0, x2 4. Second point for first constraint is 3 and 0. x1 is 3. x1 is 3. So this becomes my first constraint. This is our first constraint. What about my second constraint? First point is 0 and 3, x1 0, the other point being 3, 4 and 0. This becomes my second point. Now this is my second constraint. Fine. Now these are equalities because these are lines. Actually the first constraint was not an equality, rather it was less than 12. So it was a less than kind of constraint. Less than is towards origin. You have your constraint plotted, then towards the origin area is supposed to be less than. This is my first constraint. Towards the origin is this area. This is my first constraint and this is my second constraint. So everything towards the origin would be less than. On the line it is equal to. On the line it is 4x1 plus 3x2 is equal to 12. But I need less than. So less than would be everything towards origin. From 1 everything towards origin. But yes, remember this area is not applicable for us. Why? Because x1 has to be greater than 0, x2 has to be greater than 0. So out of the 4 quadrants, x1 and x2 are greater than 0. If I come here, x1 is less than 0 and x2 is greater than 0 in this area. But I need both to be positive, both to be greater. This is the quadrant where x1 is greater than equal to 0, x2 is greater than equal to 0. This is an area where x1 is less than equal to 0, x2 is less than equal to 0, because we have our origin over here. And here x1 is greater than equal to 0, but x2 is less than equal to 0. So all these three areas are rejected. Why are they rejected? Because all these three areas are not accepted according to our non-negativity or physical constraint. So these areas are rejected. I will be dealing only in first quadrant. Where is my first quadrant? This is my first quadrant. So my area remains only this much. If I look at here, everything from constraint 1 towards origin. This is everything from constraint 1 towards origin. What is it? If we try to mark these areas, can we mark them as, this is an area which is acceptable for constraint 1 because it is towards origin. This is an area which is acceptable for constraint 1. If I talk of this area, here I have my constraint 1, this is away from origin. I need to come towards origin. So when I take this first constraint, there are only two areas which are towards origin and of course greater than 0. And then if I talk of second constraint is, I have plotted an equality. This is an equality. But the constraint is of type less than. Less than is towards origin. Let me take this second constraint. Towards origin would be this area. So this is a feasible area according to second constraint. This is a feasible area according to second constraint. So ultimately, what is my completely feasible area according to all the constraints? Both 1 and 2 agree to this area. This is an area which is my feasible area. Can I put down my corner points over here? This is O. Let this be A, B and C. So corner points of my feasible area are O, A, B and C. This is my feasible area. Why is this feasible area? Because 1 is also accepting this as feasible, 2 is also accepting this as feasible. So all my constraints are accepting this as feasible area. So this is my feasible area. Right? Now let us remove this and explore it further. This is my feasible area. Okay, I am accepting this as my feasible area. Now, let me have point corner point, you can call the value or coordinates. And then we can have Z max. What are the corner points? 0, A, B and C. Sorry, O, A, B and C. What are the coordinates? 0, 0. 0 and 0. For A it will be 3, 0. For B will determine, for C it will be 3, 0, 3. X1 is 0, X2 is 3. C it will be 0, 3. For B, B is actually intersection of point 1 and point 2. Constraint 1 and constraint 2. Constraint 1 is 4x1 plus 3x2 is equal to 12. Constraint 2 is 6x1 plus 8x2 is equal to 24. Now, if we solve them simultaneously, I will get the solution of this point, because this is the only point common to both equations. If I try to solve them simultaneously, I will be getting a point which is common to both, which will be B. How can we solve this? Let me multiply this complete equation to, let's say 3. Let me multiply this complete equation to 2. So they get transformed. 4 3s are 12 x1 plus 9 x2 plus 36. Then this would become a 12 x1 plus 16 x2 is equal to 48. 24 multiplied by 2 is 48. Now these 12s are equal. Let me subtract one constraint from other. These will cancel. This will become minus 7 x2 is equal to minus 12. x2 is equal to minus 12 upon minus 7, making it 12 by. So x2 at this point is 12 by 7. Now that I have value of 12, x2 as 12 by 7, I can substitute in either of these constraints, either of these equalities. Let me substitute in first one. I get 4x1 plus 3 multiplied by 12 upon 7 x2 is equal to 12, making it 4x1 is equal to 12 minus, this will become 36 upon 7, making it 84 minus 36 upon 7, thereby making it 14 minus 6 would be an 8, 7 minus 3 would be a 4 upon 7. So I can get x1 is equal to 48 upon 7 multiplied by 4. This 4 goes to denominator, making it 12. Again, it is a 12 by 7. So both are 12 by 7. Can we have z, value of z? Z is 14x1 plus 16x2. 14x1 plus 16x2, 0. 14x1, I'll remove this. It will become 14x1, z is 14x1 plus 16x2. For this point, it will become 14, x1 is 3 plus 16 into 0, making it 14 3s are 42. This one would become 14 0 3, making it 48. And then this last one would give me 12 by 7 and another 12 by 7, which if we go ahead and solve it, it will become okay, we'll need, sorry, this we can cancel. 2, 12 2s are 24, plus we'll be needing a calculator for this. Okay, here it is. 16 multiplied by 12 is equal to this divided by 7. 27.42. 27.42 plus 24, giving me 51.42. 51.42. I believe this is correct. 12 by 7, 7 2s are 14, 24. This would become 27.42. 51.42. So of these corner points, which one is best? B is the best point. B is the maximum. So if it were a normal simplex problem, this would have been my final solution, that x1 is equal to 12, x2 is 12 by 7, x2 is equal to 12 by 7. But x1 and x2 should be greater than 0 and they should also be integers. So now this is the catch, this is the new issue, that they should be greater than 0 and they should be integer. I've solved this for 12 by 7, 12 by 7, but these are not integers. I need to find out integer values. So for those integer values, I'll remove this and we'll have to explore it further. Now what I'll do is I'll find out some lattice points. Those lattice points would be, of course, in the feasible area only. Those lattice points will be in the feasible area and they will be integer solutions. Here also I am having integer solutions. A is an integer solution, C is an integer solution. So as it is, I have these two integer solutions. I need to explore further. So lattice points would be all the integer values, integer combinations within our feasible region. This is an integer combination, 1 and 1. This will be an integer combination, 1 and 2, or rather 2 and 1. Then this is 3 and 0, we have already considered. Then 3 and 1 would be outside my feasible region. So I'll leave that. That is not a lattice point for me. Then 1 and 2, definitely it is a lattice point. Then 2 and 1 would again fall outside my feasible region. So these three are new additional points which could give me my best result. So already I have checked A. All these are lattice points which are integer solutions. All these will give me integer solutions. Now you can go ahead and find your Z for all these values. Now if we have a look at these, all these are integer combinations within my feasible region. But my maximum is coming at B. If I am removing this integer condition, that my maximum is coming at B. So obviously my best solution, my optimum solution lies somewhere around B. Though all these are integers, but definitely my integer solution would lie either at this point or this point or this point. Obviously these are farther. Maximization, for maximization we move away from the origin. So for maximization we are moving away from the origin. So these are the corner points away from the origin, or my best could lie on these points at most. So this is my first row where my best could lie, and this is my second row where my best could lie. This is already my best of 51.42, but this is not integer, so I am rejecting this best. Now I need to explore this and this. A and C are already explored. So I have all these three values. This is rejected because it is not integer. Now let me check these four more values. What is this? This would be 0 and 2. Let me call them 1, 2, 3 and 4. One is 0 and 2. Second point is 1 and 2. Third point is 2 and 1. And fourth point is 2 and 0. If you wish, you can include points A and C also. Sorry. One, two, three, 4. Point 1, 2, 3, 4. I am also taking A and C because these are also corner points. So let me take 3 and 0 because these are integer solutions. Integer solutions on edge of my feasible region. Integer solutions on edge of my feasible solution. So this would give me a Z. These are coordinates. These are lattice points. So Z was 14 x1 plus 16 x2. So I'll get Z of 32. This will be 32 plus 14, 46, 28 plus 16, 34, 44. Then this will be 28, this will be 42, and this will be 48. So which is the best solution? I'm getting my best solution from 0 and 3. That is 0 and 3. x1 is equal to 0, x2 is equal to 3. thereby giving me Z max is equal to 48. Because in case of A I was getting 42, C I was getting 48 as I am getting here, and these points 1, 2, 3 and 4, these are inferior as compared to point C, because C can give me 48. It can give me a Z value of 48 keeping x1 and x2 integer. So this is the idea of integer programming, that I get my best solution and then from that best solution I try to move in to an extent where I am able to get my best integer solution. From the best value I tried moving in. This was my corner area. My best obviously would have lied on these A, B and C, because O is 0, 0. So it is no good. My best would have lied somewhere here at A, B, C. It was lying at B, but it was not integer solution. So I started moving in to the next layer, point 1, point 2, point 3 and point 4. I checked them and still these are inferior as compared to C. So this C becomes my best point. Optimum solution, maximum solution, x1 0, x2 is equal to 3, giving me Z max of 48. So this is the idea of integer programming. Find the best solution and then start moving in, keeping the feasibility of the problem. We cannot break the feasibility of the problem. If I had taken a point, let's say 2, 2, then 2, 2 would have been somewhere over here. It would have broken my feasibility. If I had taken a point 3, 1, it would have been here. If I had taken a point 3, 2, it would have been here. These were breaking my feasibility. So what I do is I find my best solution and then move inwards, thereby keeping my feasibility, but trying to meet this condition of decision variables being integers. So this was an introduction of what integer programming is, what it does, how it finds the best solution and then tries to optimize keeping the solution integers. Next time when we meet, we'll solve a problem using simplex. So we'll take up integer programming using simplex method. So this is it for our present discussion. Until we meet next time, to take care. Thanks for watching. Bye-bye.